أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. Assalamu alaikum dear students. Today we're going to do the 13th lecture of operating system. In this lecture we'll discuss the final problem of IPC or inter-process communication, that was dining philosopher problem. So let us discuss what is actually dining philosopher problem and how we can approach to solve that problem. So previously we studied that the bounded buffer problem or producer consumer problem was one of the problems of IPC, and we solved that problem using semaphores. Similarly, reader writer problem and the dining philosopher problem were the other two problems in which the reader writer problem were solved in the previous lecture. While in today's lecture we'll discuss dining philosopher problem, and we'll find an approach how to solve the dining philosopher problem. So this is today's problem. In this problem you can see that there are some philosophers sitting around a round dining table, and there exists a chopstick between every two philosophers. So this is how the setting of the problem is, and this problem states that some philosophers are sitting to a round dining table, and most of the books consider the some philosophers to be 5 philosophers, 6 philosophers, or whatsoever. But here we consider some philosopher as a general term, right? So are sitting to a round dining table. Between every two philosophers there is a chopstick. Between every two philosophers there is a chopstick. A philosopher can eat its food with two chopsticks. It means for a philosopher to eat food, it needs two chopsticks, that one from the left and another from the right. For that, a philosopher must need chopsticks of both left and right. A philosopher is one of the two states, is always in one of the two states, that is eating or thinking. Either a philosopher will eat or will think. Because while thinking he might feel hungry, and once he feels hungry he will start eating, and for eating he needs two chopsticks from left and right. So we will have to ensure that no philosopher starve to death, because if also there are fewer chopsticks as compared to number of philosophers, so we'll have to find a mechanism in which proper sharing of chopstick will be guaranteed among the philosophers, so that all of them should eat, and uh, mm, no deadlock occurs. Means that, for example, one philosopher picks up one chopstick, while the another picks up another chopstick. In this case neither of the two will be able to eat. So if the chopsticks are available, then the philosophers eat. Of course philosopher eats, and if they are not available, then the philosopher thinks. If it depends, it means that the functions of philosopher depends on the availability of the chopsticks. If they are, then the philosopher will eat, and if they are not available, then the philosopher will think. This is a classical problem of process synchronization. As you may be wondering that this problem is considered with the daily life scenarios, but how it is incorporated in operating system. But in operating system, this is a really important classical problem of IPC, that not only helps us understanding the depth of the inter-process communication, but also need us to wonder about the new ways of solutions, new proposal of solutions to ensure such situations in operating system which exist among processes, because it is much in detailed process, and to decide which philosopher should eat is really a tough job. We'll discuss in a while that how difficult it is to decide that which philosopher should eat and which philosopher should think. We can present a semaphore solution to this problem. For the time being we will propose a semaphore solution for this problem, but doesn't guarantee that the dog will never occur. The semaphore solution doesn't guarantee that the philosophers will never starve to death and the deadlock will never occur. And two consecutive philosophers shouldn't try simultaneous eating. And it also very important that two consecutive philosophers shouldn't try eating simultaneously, because in that situation there will be a deadlock. A deadlock will be in scenario that either of the two will have a chopstick and none of them will be able to eat, because for eating they need two chopsticks simultaneously. So for this purpose, as our approach is to use semaphore to solve this problem. So every chopstick is a semaphore, right? Every chopstick will be called a semaphore whose value is initially 1. So every chopstick will be called a semaphore, right? Every chopstick will be called a semaphore whose value is initially 1, right? Because it is available for any philosopher to pick and eat with. uh, so we have an array of size 5. We have an array of size 5 of semaphores, right? And that is initialized to 1. It means that all the elements of the array will be initialized to 1. Here example, we will declare initially a chopstick array. Chopstick will be an array of size 5, and we will initialize all its elements to be 1, right? And the cyclic table makes it easier to find the left and right chopstick for a philosopher. And in case of linear, for example, if they were sitting in a line, then for every philosopher it would be difficult to decide where actually the left and right chopsticks are. Particularly for the first and the last philosopher. For example, if they are if these are the philosophers here, and if we are placing chopsticks between every two philosophers, so we will have to place a chopstick here, here and here, and the last chopstick may either be placed here or here. So in this situation, it will not be practically possible for this philosopher to pick up this one, and for the first philosopher to pick up the last chopstick, right? So for that purpose, the round table is being used. And for example, a philosopher is at location I. For example, it is located at location I, and choice for I is equal to 0 doesn't matter. Wherever we select, for example, if they are sitting in a around a round table, then for example, these are the philosophers, then it is totally our choice that which philosopher we are selecting to be 0 or 1. For example, this is 1, so this is 2, and this becomes 3. It is possible that we call it 0, 1 and 2. So the choice for um, initial philosopher for allotting number 1 to a philosopher doesn't matter. Then the chopstick to one side will be ith location. And if we know the number of philosopher there, for example, the number of this philosopher is 2, then the chopstick to one side will be at the second chopstick, and the chopstick to the other location will be found using the formula I plus 1 modulus number of philosophers. So I plus 1 means that philosophers plus 1, which philosopher it is. For example, it's second philosopher, so 2 plus 1, so it will become 3. And now 3 will be modeled 3 and remainder and divided by a number of philosophers. Alright, so here is the diagram in which you can see that there exists 1 2 3 4 5 6 6 philosophers are there. And for example, this is a philosopher number 1, this is 2, this is 3, this is 4, this is 5, and this is 6. This allotment of these numbers totally independent of our choice. And next, what we'll have to do is to assign a number to the chopsticks. So for example, this is chopstick number 1, this is chopstick number 2, and this is chopstick number 3, and this is chopstick number 4, and this is chopstick number 5, and similarly this is chopstick number 6. Now for example, for any philosopher, for example, we are considering philosopher number 3. For example, we are considering this philosopher, and we are actually finding the chopsticks that are adjacent to it, and apparently it looks us that 3 and 4 are adjacent to philosopher number 3. Sure, but what is the formula? How will we find the chopstick adjacent to a philosopher? So because it is the first will be at the number of philosopher. So one to the one side there will be the third chopstick, and here you can see that third chopstick is to the one side of the philosopher. And for the second side, as for using the above formula, that philosopher number plus 1 and remainder when divided by number of philosopher. So you can see that 3 plus 1 is equal to 4, and 4 modulus 6. 4 modulus 6 means that if 4 is divided by 6, then what is the integer remainder? And you can see that if 4 is divided by 6, then the integer remainder will be 4. So the chopstick to the other side will be the fourth chopstick, and here you can see that it's the fourth chopstick. Now consider the sixth philosopher. If this is the sixth philosopher, then you can see that the chopstick to the one side of the sixth philosopher will be equal to 6. So first it will be equal to 6, and for the second we'll use the formula that 6 plus 1, okay, 6 plus 1 and modulus 6. 6 plus 1 modulus 6, sorry, 6 plus 1 modulus 6. So this will be the formula to find the other chopstick for the sixth philosopher. So second is equal to 6 plus 1 is equal to 7. 7 modulus 6 is equal to 1. So as we said that to one side of the sixth philosopher, chopstick number 6 is located, and to the another side, as we calculated, it's number 1. So this is how we can find the left and right chopstick number for a philosopher. This is just a setting that you will understand the algorithm very clearly. If you are able to understand these things clearly, then you will have no problem understanding the algorithm for the dining philosopher problem. So if philosopher I wants to execute it, now we are actually moving towards designing an algorithm. So if philosopher I wants to execute or eat, then at first issues wait on two semaphores. It must issue wait call on two semaphores, that is on ith number semaphore and ith plus 1 divided by a modulus number of philosophers. So these will be the two actually values, chopsticks values, on which a ith philosopher should execute wait calls. If they were busy, then the philosopher will wait for them. Of course, if it is possible that chopstick number I and chopstick number I plus 1 and modulus number of philosopher both are busy, then in this situation the philosopher will wait. And if both of them are not busy, at least one is busy, then for another the philosopher will also wait without leaving the previous one that it has already occupied. After eating, the philosopher issues signal on both of its held semaphores. Both semaphores that were held by a process or a philosopher will be released after eating, and now they are available for another philosophers to be used. So here is the code. Here is the pseudo code which is used for by every philosopher. For example, we can say that it's an ith philosopher. So for ith philosopher, the code is this one. First, a philosopher will call wait on chopstick I. On chopstick I, philosopher will issue a wait semaphore, and then on chopstick I plus 1 and modulus number of philosophers, another call will be followed by the first one, and if both of them successfully executed, then the philosopher will eat. And once the philosopher finishes it's eating, it will have to signal on I, because it had occupied two chopsticks, so it will have to release both of them. So first it will signal I, and then it will have to signal the I plus 1 modulus n, and then it will enter in the remainder section, that is thinking. Now he will think. Now consider with the animation that how actually this code works. So for that purpose, consider we have six philosophers and six chopsticks. Initially the here is the C means the chopstick, right? So all chopsticks are initialized to 1. So C1 means that chopstick number 1 is free. It means that this the semaphore's value 1 shows that something is free. Similarly 2, 3, 4 and 5, 6, 7, all of the chopsticks are free. Now suppose at this moment P4 our philosopher number 4 wanna eat, then it must issue a call on what? Chopstick number 4. Chopstick number 4. On this semaphore it will issue a wait, and it will change it to 0, right? So and another call it will made after that, because now it was the fourth philosopher, so it occupied the fourth chopstick. Now it will have to 4 plus 1% are divided by in, so in that case it will be the fifth chopstick, so it will also issue a wait call on the fifth chopstick, and in this case its value will also be turned to 0. And now because philosopher 4 has occupied both chopstick 4 and 5, so in this case he will start eating, and now philosopher 4 is eating. All right, and for example at this moment P3 also wanna eat. Now P3 wanna eat, so it must first send a wait signal on chopstick number 3. So on chopstick number 3, when it sends a wait call, its value will be turned to 0, and again it will have also send a signal call on the fourth chopstick. But on the fourth chopstick, if it sends a call, you can see that its value is already 0. It means that it's busy, so it will be in a spin lock, and it will be trapped and wait for the 4 to be released. Similarly, for example, 1 1 then in this case it will have to it will have to call wait function on 1, so it will turn to be 0, and similarly it will also issue a wait on chopstick number I plus 1 and modulus n, that is 2, so it will also be turned to 0. In this case you can see that the philosopher 1 occupied both chopsticks to the left and right, so it will start eating now. At this moment, for example, P4 finished eating, and now when it finished eating it will have to release these chopsticks that it had held previously. So C4 has been released, and similarly C5 has also been released. And as can you noticed here that C4 was philosopher 3 was in regular watch of the what of the semaphore C4, and once it notices that its value has been incremented to 1, and it means that now it's available, so it immediately call that wait on that particular semaphore, and will turn its value 0, and now will start eating. Alright, so this is how basically this semaphore is used to govern the classical problem of dining philosopher. Now considering the example, in this situation you can see here that let's see how the philosopher sorrow and how deadlock occurs. Initially when we were discussing this problem, then I had told you that although semaphore proposes a rudimentary solution for the dining philosopher problem, but it doesn't provide a complete and perfect solution, because there exists the possibility of starvation as well as the possibility of deadlock, because both of them are interrelated if they are concomitant of each other. So for example, at this moment, all philosopher issue weight on their right chopsticks. So philosopher one basically calls for calls weight on chopstick number one. Similarly, philosopher 2 calls weight on chopstick number 2. Similarly, philosopher 3 calls weight on chopstick number 3, and philosopher 4 calls chopstick weight on chopstick 4, and similarly all of them are calling chopstick to their right. So in this situation, all of them are simultaneously calling the weight function on one of the semaphores, and you can see that if all of them have been simultaneously called, so all's value will be changed to 0. And now it's time for them to call for the another semaphore, because for example, for philosopher 1, the this chopstick has been occupied, but this has not yet been occupied, and it will have to issue weight for this chopstick as well. And this chopstick has been held by this philosopher, and this philosopher has also been issued a weight call for this, but that was held by the third philosopher. In this way, a cycle has been formed. One thing that most of the students ask is that, as I said that all of them calling simultaneously, as I said that they are calling weight function simultaneously, but initially when we were discussing semaphore, then one thing that we had clear was that no two processes can simultaneously enter the weight function, because that is the atomic operation of the semaphore. But remember that this time the semaphores are different. So does it mean that weight will be called for one semaphore, and that weight will be blocked for all other semaphores? No, only for that particular semaphore which has been called, that for that semaphore another process will not be able to enter into the weight function or signal function. So of course it is true that weight and signal are atomic operations, and only one process can run at a time, and that interrupt for that particular function has been disabled. But if there is another some another semaphore, and a process wanna execute the weight function for that semaphore, then there is no restriction. But here you can see that we have here we have six semaphores, and P1, that is philosopher number 1, was basically executing wait call on 1. Similarly, philosopher 2 was executing wait call on semaphore 2, and similarly third philosopher was calling wait on semaphore 3. So there were different semaphores, and if there are different semaphores, then all calls could be made simultaneously. But in this situation, when all of them called, and once they call another time, because everyone will ask for the next chopstick, everyone have got one chopstick, but now they are requesting for the another chopstick that is to the left of them, and all of them called, but all of them have been already occupied, and now it is a starvation and deadlock. Why? Because neither of the philosophers will be able to, none of the philosopher will be able to eat, because all the chopstick have been occupied. And in case this is called deadlock. And starvation means that all of them will wait. Definitely everyone will have to wait, because the wait has been called on this. So process number 1 is waiting for process number 2 to release. Process number 2 has been waiting for process number 3 to release. Process number 3 has been waiting for process number 4 to release the chopstick, and similarly process number 4 has been waiting for the process number 5 to release the chopstick, and process number 5 has been waiting for the chopstick to be released by the philosopher number 6. And philosopher number 6 is waiting for release of the chopstick by philosopher 1. So this is a deadlock, a spin lock loop, and in which no process or no philosopher will be able to proceed. And here you can see that all will be in the waiting style. This is basically the end of enter process communication chapter or process synchronization. So far we discussed in detail that what is a process synchronization, what is a critical section, what is race condition, how process communicate with each other, what are the ways, what are the inconsistencies that could be rendered by more than two processes executing same piece of code. Then we propose solutions and the different forms, that is binary semaphore, and then counting semaphore, and similarly we discuss some other standard algorithm like Bakery algorithm, Decker algorithm, Peterson algorithm, and eventually we discuss classical problems of IPC, that reader writer problem, that producer consumer problem, and finally today's we actually end this chapter, that is dining philosopher problem. But one thing that is remaining is the hardware solution to the inter process communication, and for you that you will have to discuss that. Inshallah, in the future I will make a video on that, but for you it's so here is an assignment for you: test set lock TSL and monitor a hardware mechanism to solve critical section problem, right? So discuss in detail with examples and pseudocode both TSL, test set lock, and monitor. Discuss them in detail using TSL. Propose solutions to producer consumer problem. We have already solved producer consumer problem for using semaphores, and for example binary semaphore and counting semaphore. With multiple ways we had solved this problem, but for you it's an assignment to solve the producer consumer problem using TSL, and using monitor propose solution for dining philosophers. So just like today we discuss use of semaphore to solve the dining philosopher problem, and you will have to propose monitors to solve the dining philosopher problem. And but in today's solution, one thing you should know that today is we had actually not solved the problem, because at the end we found that with our proposed solution the system goes to deadlock, and all philosophers are basically starved to death. So the deadlock prevention and deadlock avoidance and deadlock recovery algorithm will be discussed later when we start deadlock chapter. But for now you should compromise on the incomplete solution of the dining philosopher problem. Thank you so much. Take care. Khuda Hafiz.